We're going to finish the chapter on electron configurations, and we're going to specifically talk about electron configurations and see some examples of how we would write out the electron configurations. Then we're going to learn about what are called orbital box diagrams, where we use boxes to represent the orbitals and fill them with the electrons that we know go there. And then we'll learn about the electron arrangements of monatomic ions, and then finish off with some trends that we see in the periodic table. Let's get warmed up, a little bit of review. We're told an unknown gas diffuses 2.828 times faster than oxygen at the same temperature and pressure. What is the molar mass of this gas? Okay, well, our primary equation, the square root of the molar mass of our unknown to the molar mass of O2 is equal to the rate ratio of the O2 to the unknown. Well, where's that 2.828 go with the faster gas? And the faster gas is the unknown gas. So let me go ahead and replace the unknown with that 2.828, and let's go ahead and square both sides and then multiply out the molar mass of O2. And here's the molar mass of our unknown isolated. Let's go ahead and square that 1 over 2.828 and bring out the molar mass of O2, which is the 32.0 grams per mole. And we see that we have 1/8 of the molar mass of oxygen for a molar mass of 4 grams per mole. I would remind you that at any time you can stop the video, do your own work, and then compare your work to mine. Okay, what is the average velocity of nitrogen molecules in the atmosphere at room temperature? Well, our primary equation is the velocity of the gas equation. The velocity squared is equal to 3RT over the molar mass. Let's take the square root of both sides. And now we do have the 3, the R, the T, and the molar mass, so we have everything that we need to plug in. And I would remind you that the version of the universal gas constant here is 8.31 times 10 to the third gram meter squared per second squared over mole kelvins. Again, we have everything that we need, and note how all units cancel, grams cancel, moles cancel, kelvins cancel, and then we get the square root of meter squared over second squared for the appropriate units of meters per second. At what temperature will the average velocity of nitrogen molecules be twice their average velocity at room temperature? Well, our primary equation of the velocity of gases at two different temperatures is the square root of T2 over T1 is equal to the velocity ratio of the gas at temperature 2 and 1. We're solving for T2, so let's take the square of both sides and then multiply out T1. And here's T2 isolated. And even though we don't actually have the velocity of these two gases, we have their ratio, a 2-to-1 ratio. So essentially we have 4 times the absolute temperature in kelvins for 1180 kelvins. We're asked to calculate the energy from the ultraviolet line in the mercury spectrum with a wavelength of 403.8 nanometers, and we want our answer in kilojoules per mole. Remember, we'll initially get our answer in joules per photon, and then we'll use our units to convert that into the specific units of kilojoules per mole. Okay, well, we're after the energy, and our equation for energy is delta E is equal to h nu. And we don't have nu. We'll get that from the wave equation, where lambda nu is equal to c, or nu is equal to c divided by lambda. Either we remember the speed of light, we use that a lot, or you can expect that to be given to you on the exam. Lambda given, and again, make sure that your wavelength is going to be in meters so that those units match. If you didn't put it into meters and you paid attention to your units, you would catch that mistake right now. So it's always worth putting your units in and keeping track of your units, even if we don't use our units expressly to set up the calculation for us. Okay, so we have our new frequency, Plugging that into our equation, E equals h nu. H, Planck's constant, would also be given to you. And note that the seconds and reciprocal seconds cancel to give us the answer of joules. And again, that's joules per photon. We'll be using our units for the second part to actually convert this into kilojoules per mole. Step 1. Step 2, we're starting with that just calculated 4.919 times 10 to the negative 19 joules per photon. And now step 3, let's get out of joules. Yes, we can go straight to kilojoules. Then out of photons, yes, we can go to moles of photons. I hope you found all these steps very easy. 1 kilojoule, 10 to the positive third joules, base 10 number, still going with the base unit. And Avogadro's number of photons per each mole of photons. And when I put this on my calculator, I come up with 296.3 kilojoules per mole. Is this a reasonable answer? Yes, it is. Okay, what wavelength of light is absorbed when a hydrogen electron moves from the ground state to the third principal shell? Okay, we only have one equation for wavelength, and if you get stuck with what's going on, go with what are you after? We're after the wavelength of light, and we only have one equation for wavelength. Lambda nu is equal to c. Let's solve for lambda. Now we have c, but we don't have nu. Where are we going to get nu from? From the energy of light, where E equals h nu. And let's solve for nu. Do we have the energy? No, we're going to get that from Planck's equation, which states that the change in energy between two electron transitions is equal to the negative Rydberg constant times 1 over n high squared minus 1 over n low squared. N high would be what? The third principal shell, so 3, and n low would be what? The ground state, where n low is equal to 1. I would do the division first, so 1 divide 3 squared minus 1 divide 1 squared, hit equals, then multiply the negative 2.180 times 10 to the negative 18 joules, and that should give you 1.938 times 10 to the negative 18 joules. Make sure that you practice these calculations. Sometimes we think that we have no problem putting them on our calculators, and then later we find that we do. So practice using your calculator as well. Okay, now we have the energy, and so that just calculated energy divided by Planck's constant, and that gives us our frequency of 2.925 times 10 to the 15th reciprocal seconds. Plugging that into our original equation, we have the speed of light. We just calculated nu. Putting this on my calculator, do note how reciprocal seconds cancels for both to give us the appropriate units of meters. Does this answer make sense? A wavelength in hundreds of nanometers does seem reasonable. Be somewhat on the quite short wavelength range of visible light. Actually, I believe visible light is 400 to 800 nanometers. So this would actually be in the ultraviolet range. And now, what are the possible values of m sub L? Remember, that is the orbital quantum number for an S subshell. Well, for an S subshell, L is equal to 1, and m sub L, L is equal to 0, and m sub L goes from negative L to positive L, including 0, and hence 0. For a P subshell, well, now L is equal to 1, and so m sub L goes from negative 1 through 0 to positive 1, or negative 1, 0, and positive 1, indicating the 3 orbitals and their quantum numbers for the P subshell. For the D subshell, L is equal to 2, and so we go from negative 2 through 0 to positive 2 for 5 orbitals, negative 2, negative 1, 0, 1, and 2. for an F subshell, L is equal to 3. So we go to -3 through 0 to +3. And this would be the 7 values of the orbital quantum number. And what about where all sublevels where n is equal to 2? Well, we either have, remember for our angular quantum numbers, L goes from 0 through n minus 1, so we have either 0 or 1. And so where L is equal to 0, we simply have m sub L equal to 0. Where L is equal to 1, m sub L goes through from -1 through 0 to +1. And hence these are the orbital quantum numbers for the 1s orbital, meaning the singular s orbital, and the 3p orbitals. Remember, the p subshell always has 3 orbitals. Okay, on to electron configurations. We've actually looked at this and been working towards this. And first off, I want to point out that we're going to be using the periodic table to answer all the questions that we need. Now, we need a little bit of practice with how we go about writing this all, and I've already indicated where the S's, the P's, the D's, and the F's are. There's only going to be one other thing that we need to know, and that is when we hit our first S, which is that. When we hit our first P, which is that. Let me remind you that the S block included group 1A and group 2A. The P block included group 3, 4, 5, 6, 7, and 8A. And then the D block were the transition elements. And then the F block were the inner transition elements, the guys at the very bottom. So remember where the S's, P's, D's, and F's are, so we already know half of what we need to know to use the periodic table. The others to know when we hit each of these for the first time, which one is it? And so the first time we hit an S, that will be in shell 1, so that's 1S. Our first P shows up in shell 2, so 2P. Our first D in shell 3 for 3D, and our first F shows up in principal shell 4 for 4F. So our first S, 1S, our first P, 2P, our first D, 3D, and our first F, 4F. And you may recall that the number of subshells in a principal shell was equal to the principal quantum number. So principal quantum number 1 says there's only one subshell, and that would be the S. Principal quantum number 2 says there's 2 subshells, S and P. Principal quantum number 3 says there's 3 subshells, S, P, and D, and only when we get to the 4th shell will we finally be big enough to hold S, P, D's, and F's. Now, armed with these 2 pieces of knowledge, essentially it turns any periodic table, which you always have available to you. You always have a periodic table available on your exams. And it will turn any periodic table into this. So again, the left shoulder are S's, the right shoulder are P's, the guys in the middle are D's, the guys at the bottom are the F's. And we see that the first S is the 1S, the first P is the 2P, the first D is the 3D, and the first F is the 4F. Now while we have this up here, let's do a quick exercise. Break out your periodic table and locate bromine. Okay, bromine, element 35. We want to do the electron configuration of bromine. So, what is the first subshell that we occupy? And we go to element 1, we see it's in the S, and our first S is 1S, and that'll get 2 electrons. So we have 1S with 2. There's 2 electrons. Where's our third electron? Well, that's in the S below it. That's 2S. And that fills with 2 electrons. So we then had 2S, 2. There's 4 electrons. Where's our fifth? Well, that's over there in the P block, and the first P is the 2P. And if you forget, count. How many does it take to fill up? 1, 2, 3, 4, 5, 6. So 2P, 6. We're up to 10 electrons. Our 11th electron, starting 3S, that gets another 2. Our 13th electron starts another P. Again, the P's will get 6 when they fill up. There's 18. Our 19th electron starts another S. That'll get 2. Then our 21st electron goes where? Well, if you look at the screen, you see it starting the 3D. We knew these were the D's, and we might be tempted to call them the 4Ds, but no, they're the 3Ds. They get buried down underneath that outer shell. And so there's your 3D, and how many electrons go into the 3D? Well, if you forget, just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 go into 3D. And then to our 4p, and actually bromine is going to be within the subshell, so let me count. 1, 2, 3, 4, 5 electrons gets me to bromine. So real quick, we had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And that's the type of notation that we're going to be using. Let me introduce you to that here. And so here's the first 10 electrons, 1s2, 2s2, 2p6. So let me point out that the number out front is your principal quantum number. The letter represents the subshell, your angular quantum number. And then the superscript is the number of electrons that are actually going into that subshell. Now, we saw what's called energy overlap, and that's essentially that we didn't do all of the third shell all at once. We didn't go 3s2, 3p6, 3d10. No, we had the 4 s's in there as well. But the periodic table told us that, so we didn't have to worry about that. So we don't really need to know anything about the energy overlap, except for when we encounter it and it seems odd, that indeed it is odd, if you want to call it that, but we know how to treat it because the periodic table essentially told us that that was not going to be the 4d, it was the 3d, even though it followed the 4s. Here's an energy diagram to illustrate the energy levels. So 1s at the bottom, then 2s, then 2p, 3s, 3p, 4s, 3d, 4p, and then onwards. And there'll be actually some other guys in the, after 4p in between them and 4d. But the point of the matter is we saw that our lowest energy level was the 1s, so we put our first electrons there, then our 2s, then our 2p, then our 3s, etc. And we would continue in that fashion to fill them up. Okay, let's do some examples where we're asked to give the electron configuration of the following, and we're going to begin with oxygen. Okay, well, I think I'm going to draw a picture of this to remind us where the electrons go. And so, where does that first electron go? Into the 1s. That fills up with 2. My third electron goes into the 2s. And that fills up with 2. There's 4 electrons. My fifth electron starts my 2p. And I actually only have 4 more electrons, and so we're not going to fill up the 2p. We'll only have 4 that fill it up. So we had 1s, and that got 2. Then our 2s, and that got 2. And then our 2p, which got 4. Next we're going to do phosphorus with 15 electrons. So let's take it from the diagram we see here, and let's go ahead and assume that's filled up. So we would have 10 electrons there. So our 11th electron is starting another s. That'll be the 3s. That'll get a 2 to fill it up, so there's 12 electrons. Our 13th electron starts another p. That'll be our 2p. And that could fill up with 6, but we only have 3 more. So we had 1s, got 2. Then 2s, got 2. Do note, anybody with 2 or more electrons has 1s2. Anybody with 4 more electrons has then 2s2. Then anybody with 10 or more electrons has 2p6. Anybody with 12 or more then has 3s2. And then, as I mentioned, we weren't able to finish that 3p with all 6. We only had 3 more electrons, so it got 3. Now, there's a way we can double check to make sure we didn't make any mistakes. Let's count those electrons. So we had 2 and 2 and 6 and 2 and 3. 2 and 2 and 6 is 10, and 2 and 3 is 15. So yeah, we've got all 15 electrons. So we can always double check when we're done by counting those electrons. Okay, let's add another 20 electrons, and so let's finish off with taking this from the 3p being filled up, so that would be 18 electrons. My 19th electron is starting 4s, and that gets 2. My 21st electron is starting my Ds, and the first Ds are the 3 Ds. Note all that empty space down there in that third region of space. Okay, and that fills up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're up to 30. Our 31st electron is starting another P, so it's time for our 4 Ps. And we're going to just about fill this up. And so we had 1s2, 2s2, 2p6, there's our first 10, 3s2, 3p6, there's our first 18, 4s2, 3d10, there's our first 30, and then we have just 5 more for 4p5. Again, we can always count them to make sure we've made no mistakes, and I recommend that you do while you're first getting the hang of this. Okay, next let's do platinum. And actually, I've exhausted my my model. Okay, but we do know where the first 36 electrons go. We have a visual of the first 36, so we're going to be okay with them. So let's just pick it up with the 37th electron. So we're starting another S. That'll be the 5s, and that'll get 2. Our 39th electron starts a D. The last D was 3D, so this is 4D. That'll fill up with 10. There's 48. 49 starts another P. That'll be the 5P. That'll fill up with 6. We're up to 54. Our 55th starts 6s. Fills up with 2. Now, let's look at the next one. We have 57, and then a guy right next to it is 72. What happened between 57 and 72? Well, that's where the F's come in. So after we put that 1 electron into the 5D, we're going to come down and put 14 electrons, we can always count till we forget these numbers, into the 4F. That'll bring me up to 71, and I'll continue with 72. And actually, we're still in the 3D for 1, 2, 3, 4, 5, 6, 7 more. So again, our first 36 are going to look very similar to where we left off with bromine. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Then we went on to 5s2, 4d10, 5p6. That got us to 54. 6s2. Then we hit 5d for 1. Then we did the 4f14. And then we came back for another 7 in the 5d. You may note that on the PowerPoint here, I have 4f14 and then 5d8. If you're going to lump all of your d electrons together, and a lot of my associates teach their students to do it this way, then I would just ask that you make sure that those Ds, those 5 Ds, come after the Fs, the 4 Fs. Now, why would you want to do this when the periodic table tells you otherwise? There really is no reason other than it's a little bit less chicken scratch, meaning you don't have to write 5D twice. So I really don't recommend this because the periodic table doesn't tell you that. So again, after 6s2, I would have done 5d1, then 4f14, and then 5d7. To me, that's the superior way to do it, but you may have already learned in a previous class to essentially lump your Ds all together, and that'll be acceptable. So I accept both ways. Okay, on to what I consider a simple concept, and this is orbital box diagrams. And this is where we use a box to represent the individual orbitals, and then we're going to populate these orbitals with electrons, and we're going to use arrows to represent those electrons. Now, we're going to use arrows because we're going to have an up arrow and a down arrow to represent the opposite spinning electrons that go into a orbital. Okay, so let me show you an example using carbon. And so carbon, this would be your 1s2, 2s2, 2p2 electron configuration. And do note, when I have two electrons in the same box, I have one up and one down. When I have individual electrons, and do note I didn't pair that second electron in the 2p because there's a little bit lower energy going into an empty orbital than to pair up. And by convention, we would show all unpaired electrons pointing the same way. Okay, let's do some examples. You have the orbital box diagram for the following, and we have oxygen and an atomic number of 8. It says we have 8 electrons. And we know that we're going to put our first two in the 1s, and one will go spinning up, and the other one goes spinning down. So one arrow up, one arrow down. Then I fill my 2s. So again, one arrow up, and one arrow down. There's 4 electrons, and I have 4 more. So I'm going to put 1, 2, 3 up, and then the fourth one, I'm going to join one of these going down. So there are the 8 electrons around a neutral atom of oxygen. Next we have sodium, and it fills its 1s, so one up and one down. It fills its 2s, so one up and one down. And it's also going to fill its 2p, so in each of these 3 we have one up and one down. There's 10 electrons. For our 11th electron, I'm going to have one arrow in my 3s. And do note the electron configuration of sodium: 1s2, 2s2, 2p6, 3s1. We did phosphorus earlier, and we saw 1s for 2, so one up, one down. 2s for 2, one up, one down. 2p for 6, so one up and one down in each of the 3. 3s got 2, one up and one down. And then 3p got 3, so all 3 pointing up. Now if you point the individuals up or down, it's not going to really matter. Just be consistent. I always do them up. And only draw the paired one down. As long as you don't have both of them up or down, it's really not going to matter. Okay, next we have argon with 18 electrons, and so 1s fills up with 2, one up, one down. 2s fills up with 2, one up, one down. 2p fills up with 6, so all 3 get one up and one down. 3s fills up with 2, one up, one down. And 3p fills with 6, so again all 3, one up and one down. Okay, onto the electron arrangement of monatomic ions, so single atom ions. Now for the main group elements, so we're talking about the left and the right shoulder, our S and P block elements, we expect that when they form ions, they're doing so to achieve the electron configuration of their nearest noble gas neighbor. And so we can just ask, what is the nearest noble gas neighbor? And that tells us what they're doing. So let's go ahead and talk about sulfur. What is the closest noble gas to sulfur? And that would be argon. Do note sulfur has 16 protons and 16 electrons. And what's closer, neon with 10 or argon with 18? And argon with 18. So it wants to be like argon, so it's going to gain 2 electrons. What about magnesium? Well, magnesium has an atomic number of 12, so it has 12 protons. And in this case, neon is closer with 10, so it's going to lose 2 electrons to be like neon with 10. So as some examples, we have nitrogen, and here is the electron configuration of neutral nitrogen. Now, those noble gases have their outer electron configuration filled. So that means that they filled up that 2p subshell, or should I say their outer p subshell. And so that 2p wants six electrons, and so nitrogen wants to gain 3 electrons in order to fill it. And in doing so, it now has the electron configuration of neon, its nearest noble gas neighbor. And again, if we did the electron configuration of all the noble gases, essentially they have completely filled their outer shell. For helium, he would just have 2 electrons in its 1s, but for everybody else, they're going to have 6 electrons in their outer p's. Okay, oxygen with its 8 electrons. Here's its neutral electron configuration. Now, what does oxygen want to do? Well, what's the closest noble gas to oxygen? And that again would be neon. This time he needs 2 electrons. Once oxygen has gained 2 electrons, those 2 electrons join the 4 in the 2p, and now we have, once again, the electron configuration of its nearest noble gas. So when elements are reacting, the main group elements, they're achieving the electron configuration of their nearest noble gas neighbor. That's what elements want to do when they react. Elements want the electron configuration of their nearest noble gas. The noble gases are inert. They don't react, and they don't react because they have very stable electron configurations. There's something special about having filled that last shell. And everybody else wants to do the same. Okay, we did magnesium earlier, and so here's the electron configuration of magnesium. And it's going to be a lot easier for magnesium to lose 2 electrons to become like the last noble gas. You do know that's also neon. So for each of these elements, neon was the closest noble gas. And so when they're done forming their ions, when they're done reacting, they have the electron configuration of that noble gas. Now the transition metals are just a little bit different. When the transition metals, and by the way, metals are losing electrons, nonmetals gain electrons. There's something that's helpful for us to recognize. Metals lose electrons. Nonmetals gain electrons. Metals were to the left of the zigzag. Nonmetals are to the right. When the transition metals lose electrons, we need to know that when they do so, the entire outer s subshell collapses. Even if you just took one of the 2 electrons, essentially both of them go away, and now any remaining electrons are going to populate that last d subshell. And now they'll be on the outer side because the s's are no longer there. So as an example, we actually have 2 ions of iron. And here is the electron configuration of a neutral iron atom. And now let me introduce you to a shorthand notation. That argon in square brackets is essentially saying this is a shorthand representation for all the electrons represented by argon. In other words, this represents the first 18 electrons, so I don't have to worry about drawing in all those electrons. So this is the shorthand notation where you would draw the preceding noble gas elemental symbol within square brackets, and then that represents all those interior electrons, and then you would only show the outer electrons. Okay, now iron forms a +2 ion, and so it's going to give up 2 electrons. And as I mentioned, if you're going to lose any electrons, even if it's just 1, you're going to get rid of all of those s electrons. And so we no longer have the 4s subshell. Now, do note, neutral iron has 26 electrons. If we lose 2, it has 24. That's 6 electrons beyond argon with 18, so all 6 of them go into that 3d subshell. So that's a quick and easy way we can tell just how many electrons are going into that 3d subshell. Iron also forms a +3 ion, so it's going to lose 3 electrons. And so now it only has 5 electrons beyond argon, and all 5 of those electrons go into the 3D subshell. Okay, I'd like to go over some periodic trends that we see, and we have 3 trends that follow the same pattern, and that's going to be atom size, ionization energy, and electronegativity. Again, they're all related to each other, and we'll talk about that when we get to them. Okay, well, let's first talk about the sizes of atoms, and it should make sense as you're getting bigger and bigger and bigger as you go down in a group. So you're getting more and more outer shells. Now, what may not make a lot of sense is that you would actually be getting smaller as you proceed to the right across a period. So essentially what we have is the smaller atoms are up and to the right. Well, why would we get smaller as we're going across a period? Well, it's because we have more and more protons pulling on the outer electrons. Now, the outer electrons are feeling what's called the shielding effect, meaning they're feeling the repulsion due to the interior electrons, so they're not really feeling the entire pull of the nucleus. But as you're going across a period, you still have the same amount of shielding effect, but now you're just getting more and more and more positives in that nucleus, pulling in those outer electrons more and more intensely, and hence getting smaller and smaller as we proceed across that period. And here is some examples of some atoms, and we can see indeed that we have our smallest atoms up and to the right. We indeed got smaller as we proceeded to the right across a period. Now, when it comes to the sizes of ions, let's see if we can predict this. What's going to happen to our size if we gain electrons? Well, we're actually going to swell up a little bit, so we're going to have a bigger size for negative ions in the neutral atom. And what if we lose electrons? Well, then we're going to shrink a little bit. So I hope it makes sense that negative ions are going to be larger than the neutral atom, and positive ions are going to be smaller than the neutral atom, especially if we got rid of that outermost shell. That should definitely tell us we should have a smaller size. Okay, what is ionization energy? Well, that's the energy it takes to remove an electron from an atom. So essentially we're removing electrons. Now, it's going to take more energy to remove an electron from an atom that's small, because there's a greater pull of the outer electrons if you have a small atom. As you get bigger and bigger and bigger, there's a weaker attraction to those electrons, because those electrons are further and further from the nucleus. If you're familiar with gravity, as you get further and further and further from the body that you're gravitationally attracted to, essentially your attraction to that drops off. Actually, it's a square function. So if you were twice as far from, let's say, a planet, then you would have 1/4 of the gravitational attraction. It's the same thing for the attraction of an electron to the nucleus. If you're twice as far away from the nucleus, you're only going to feel 1/4 the attraction of the nuclear pull. And that's also not taking into account the interior electrons. So it should make sense that the smaller atoms are going to have a higher ionization energy. Then we have electronegativity, which is the tendency or the ability of an atom to attract additional electrons. And additional is the key word here. So we saw how oxygen wants to gain more electrons. It wants to gain additional electrons beyond its normal neutral amount. And we're going to see that, again, those smaller atoms can attract electrons much more intensely than the bigger atoms. And so what we're going to see is all 3 of these following the same trend. A decrease in atom size, an increase in ionization energy, and an increase in electronegativity all proceed up and to the right of the periodic table. So up and to the right we have the smaller atoms, the highest ionization energy, and the highest electronegativity. Now remember that definition of electronegativity and the concept of electronegativity. Elements, some elements, fluorine actually being the most electronegative element, we're not counting the noble gases because they already have the electrons that they want. Fluorine is the most electronegative element, and it's so strong at attracting electrons that it can force some elements to bond that don't want to bond. For example, some of those noble gases can be forced to bond by fluorine. And again, it's because of that very high electronegativity. We'll talk more about electronegativity in preceding chapters. Okay, let's practice some of the things that we've learned here. Give the electron configuration of the following, and we have fluorine with 9 protons and hence 9 electrons. We'll grab your periodic table, and where's the first electron? And that's going to be in the 1s, and that fills up with 2. We're up to 2. Our third electron starts 2s, and that fills up with 2. There's 4. Our fifth electron starts 2p, and fluorine is within the subshell, so 1, 2, 3, 4, 5 gets me to 9 electrons. So again, that was 1s2, 2s2, 2p5 for 9 electrons. Next we have chlorine with 17 electrons. Well, we know where our first electron is. 1s fills up with 2. Then 2s fills up with 2. Then 2p fills up with 6. We're up to 10. 11 starts 3s, fills up with 2. 13 starts 3p. And for chlorine, that's also going to be another 5. So again, that was 1s2, 2s2, 2p6, 3s2, 3p5. If you count them, we have 17 electrons. And I recommend that you do count these to make sure that you've made no simple mistakes, like forgetting the 3s2. Next, let's do bromine. And so we know where those first 18 electrons are. 1s2, 2s2, 2p6, 3s2, 3p6, and I'm just looking at the chlorine we just got done with. So again, our first 18, 1s2, 2s2, 2p6, 3s2, 3p6, it would fill up. Okay, so there's 18. Our 19th electron goes into 4s2. Then our 21st electron, if anything's going to foul us up, it's this guy. And where does this electron go? 3d, and that fills up with 10 to get us to zinc. And then our 31st electron puts us into 4p, and that's going to get another 5. So again, 1s2 for anybody with 2 or more electrons, 2s2 for 4 or more, 2p6 for 10 or more, 3s2 for 12 or more, 3p6 for 18 or more, 4s2 for 20 or more, 3d10 for 30 or more, and then we had 5 more that went into the 4p for 4p5. And again, if you add these all up, we have 35 electrons. And who would you guess I'm going to do next? Iodine with 53 electrons. Okay, well, we know where the first 36 are. So again, if we filled up that 4p with 6, then we know where our first 36 are. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay, that gets us to 36. So we only need to pick it up from there. 37 starts, 5s gets 2. 39 starts, 4d picks up 10. And then 49 starts 5p, and there's only going to be 5 electrons to go in there. So again, that's 1s2, 2s2, 2p6, there's your first 10. 3s2, 3p6, there's your first 18. 4s2, 3d10, 4p6, there's your first 36. 5s2, 4d10, and now I only had 5 more electrons for 5d5. Now I hope that you notice that what these four elements have in common is they're all the halogens. They're all group 7A elements. And they all are part of the same group, the same family, and they react very similarly. And we can see why, because they all have 5 electrons in that last p subshell. And they all needed just one more to fill it up to be like that next noble gas. And I hope we're seeing how this is relating to chemical reactivity and why elements are reacting the way they do so that they can obtain the electron configuration of those very stable noble gases. Okay, let's give some orbital box diagrams, and we're going to begin with nitrogen, which has 7 electrons. It's going to fill up the 1s, so 1 arrow up, 1 down. It's also going to fill up the 2s, so 1 up and 1 down. There's 4 electrons, and it has 3 more, so I'm going to put 1 individually into each of the 2p orbitals. Okay, next is neon with 10 electrons, so it's going to fill up the 1s, 1 up, 1 down, and the 2s, 1 up and 1 down, and it's actually going to fill up the 2p as well. So all 3 orbitals get 1 up and 1 down. And here we can visually see those 10 electrons. Okay, aluminum has 13 electrons. Well, we're going to fill up the 1s. 1 up, 1 down. We're going to fill up the 2s. 1 up, 1 down. And we're going to fill up the 2p. So each of the 3 gets 1 up and 1 down. There's 10. I still got 3 more, so I'm going to fill my 3s. So 1 up and 1 down. 1 more. So let me just put into one of those 3 orbitals. Okay, next we have sulfur with 16 electrons, so we fill up the first s, so 1 up, 1 down, the 2s, 1 up, 1 down, and we fill the 2p, so all 3 get 1 up and 1 down. We also fill up the 3s, so 1 up and 1 down, and now we're up to 12. We've got 4 more, so I'm going to put 1, 2, 3 up, and then the 4th one joining the first one going down. Okay, similar question. We're going to use the shorthand notation though. So for chromium with 24 electrons, well, I don't need to worry about the first 18. So I have 6 more electrons to place. So I'm going to fill up the 4s, so 1 up and 1 down. And then I've got 4 more, so 1, 2, 3, 4 pointing up. What about the chromium 2 ion? Well, now I've only got 22 electrons, which are 4 electrons beyond argon, and none of them go in the 4s. All 4 of them go into the 3d. What about the manganese 4 ion? Okay, well, let's see. Manganese, element 25, but plus 4 means it's got 21 electrons. That's only 3 beyond argon. So all 3 are going to go into that 3d subshell. So all 3 pointing up. Again, once you form an ion of one of those transition elements, there are going to be no s electrons. Okay, next we have zinc. And that +2 charge tells us that it has 28 electrons. Neutral zinc has 30, so +2, 28. And that's 10 electrons beyond argon, with all 10 of them going into the 3D. So all 5 orbitals get 1 up and 1 down. Now give the electron configuration in principal shell notation for the following. Well, we haven't really done any examples with principal shell notation, but this is just simply saying, well, of these electrons, how many go into principal shell 1, principal shell 2, shell 3, etc. Now, we don't have any issue at all with the first 2 shells. Actually, let's say the first 18 electrons. Shell 1's going to fill up with 2. Remember that? 1s got 2. Principal shell 2 gets 8. 2 from the 2s and 6 from the 2p. And then we're going to be fine with the first 8 that go into shell 3. So let's do nitrogen, and the atomic number of nitrogen is 7. So we have 7 electrons to place. Of those 7, how many go into shell 1? Shell 1 fills up with 2. Of the remaining 5, how many go into shell 2? All 5. Next we have chlorine, and the atomic number of chlorine is 17. Of those 17 electrons, how many go into shell 1? Shell 1 always gets a max of 2. So anybody with 2 or more electrons, you've got 2 in shell 1. Of the remaining 15, how many goes into shell 2? Well, we're safe with filling it up with 8. Of the remaining 7, how many go into shell 3? And for the first 8, we're safe. And so we have less than 8. So all 7 go into shell 3. Let's do neon, and the atomic number of neon is 10. Of those 10, how many electrons go into shell 1? 2. Of the remaining 8, how many go into shell 2? 8. We completed shell 2 to get neon. We would have completed shell 1 to get helium. We would have completed shell 3, not taking into account the d electrons, to get argon, etc. Okay, now calcium. What's the atomic number of calcium? 20. So now we're venturing beyond 18 electrons. So what does that mean? Well, let's go ahead and see what happens. So of the 20, how many go into shell 1? And shell 1 holds 2. Of the remaining 18, how many goes into shell 2? Shell 2 holds 8. Of the remaining 10, how many goes into shell 3? Well, we know we're safe with the first 8. By the way, that gets us up to argon. Now, where do those last 2 electrons go? They go out into shell 4. So that's why when we go beyond 18 electrons, we need to be a little more careful with where do those electrons go when we're doing a principal shell electron configuration. We know that shell 3 fills up with 18, but they just don't come in all at once. Okay, let's go a little bit bigger. Iron, what's the atomic number for iron? 26. Of those 26, how many go into shell 1? 2. Of the remaining 24, how many go into shell 2? 8. Shell 1, shell 2, very easy. Of the remaining 16, how many go into shell 3? Well, we know we begin with 8. And then we put 2 electrons out into shell 4. Now we've got 6 more. Where do they go? Well, they're going to join the previous 8 down in shell 3. Remember, they buried themselves back underneath those 2 outer 4s electrons. And just like before, we can always count. 2 and 8 is 10, 8 and 6 is another 14, and 2 more for 26. Now give the electron configuration and subshell notation for lead, element 82. We'll grab your periodic table. And so the first electron goes into 1s, and that gets 2. Third electron starts 2s, and that gets 2. Fifth electron starts 2p, and that gets 6. Our 11th electron starts 3s, and that gets 2. Our 13th electron starts 3p, and that gets 6. Our 19th electron starts 4s, and that gets 2. Our 21st electron starts 3d. If anything's going to mess us up, it's element 21, or 21st electron. And so 3d, and that fills up with how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get to zinc. And then our 31st electron starts 4p, and that fills up with 6. We're up to 36 with krypton. Our 37th starts 5s, and that gets 2. Our 39th electron starts 4d, and that's going to fill up with 10. And then our 49th starts 5p, and that fills up with 6. We're up to 54, xenon. Our 55th starts 6s, that fills up with 2. Our 57th gives us 5d, 41. Then we drop down to the 4f's for 14. Again, if you forget that 14, just count. Then we continue with the 5d's, and that's going to get the last 9. That gets me to 80. My 81st electron starts the 6p, and I need just 2 electrons in my 5, between my 6p to get to lead. So again, that was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I hope you're following along in the periodic table as I'm doing this. 3d10, 4p6 brings us to krypton. Then 5s2, 4d10, 5p6 brings us to xenon. 6s2, 5d1, 4f14, 5d10, 9, we already did the first, and then 6p2. We can always go back and count them all, and sure enough we'll get 82 electrons. Now what if we don't get 82? Then we made a mistake somewhere. Okay, we're going to do one more, and I'm going to highly recommend that you do this one on your own first. So stop the lecture, do this on your own, and then continue when you're done. Okay, we're doing uranium, element 92. Okay, well we essentially know where our first 80 electrons go. So real quickly, and I'm just looking at what we did before. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, again that brings us to krypton, 5s2, 4d10, 5p6, bring us to xenon, 6s2, 5d1, 4f14, 5d9, and now we're going to have 6p6 to bring us to radon, and then 7s2, then 6d1, 5f, and then uranium is right there for 1, 2, 3 more. So again, the first 80 are going to be the same as the first 80 with lead. 1s2, 2s2, 2p6, there's neon. 3s2, 3p6, there's argon. 4s2, 3d10, 4p6, there's krypton. 5s2, 5d10, 4d10, 5p6, brings us to xenon, 6s2, 5d1, 4f14, 5d9, 6p6 brings us to radon, then 7s2, 6d1, 5f3 brings us to uranium. And I recommend that you go back and count those all. So I'll do that with you real quick. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 57, 71, 80, 86, 88, 89, 92. So if we count them and we got the number that we're after, we can have confidence that we did this correctly. And I hope you have no problem doing one all on your own, even though this was the biggest we've done so far. Okay, that concludes this lecture where we finished off the electron configurations. And so we learned about electron configurations both in principal shell notation, we only did a few examples of those, and in subshell notation. And then we also saw the relationship of subshell notation to orbital box diagrams. We also talked about the electron arrangement of monatomic ions, and we expect for the main group elements, so again that's our left and right shoulders, or S and P block elements, that they are going to achieve the electron configuration of their nearest noble gas neighbor. So the electron configuration of these ions should be that of that nearest noble gas neighbor. What about the transition elements? Well, they're not going to normally reach their noble gas. Some will, but they normally won't. And so essentially we need to mainly remember that the entire outer S subshell collapses, even if we are only to take one electron. And then any electrons beyond the preceding noble gas go into that D subshell. We finished off with periodic trends, and those were atom size, ionization energy, and the electronegativity. Don't forget the definition of electronegativity, the tendency of an atom to attract additional electrons. And they all follow the same trend. Smaller atoms, high ionization energy, and high electronegativity were up and to the right in the periodic table. And that concludes this lecture.